Welcome to Astronomy, Chapter 14. In this chapter, we're going to do a very entertaining section that a lot of people enjoy learning about as sort of a far-out concept in astronomy. For this chapter is going to be focused on nothing but one object that is apparently a relatively rare object in astronomy. It is, of course, the black hole. Now, a black hole, and this is entitled Matters of Gravity, is an idea about explaining the gravitational effects associated with this thing we call a black hole. And before we go too far into this, we need to explain really what is a black hole. And before we can even do that, we're going to have to explain a little bit about what happens to make the evidence of a black hole. So the beginning of this chapter actually does not talk about black holes. Instead, what it talks about is the concept of relativity. And relativity, of course, is one of the topics that was brought to us by Albert Einstein. Easily the most well-known scientist from the 20th century. Einstein was a brilliant man who really changed a lot of our understanding about the universe based off of this concept, especially the idea of special relativity. And the idea is that the one that really matters here is that the idea of the speed of light being a constant, and what happens if you are moving at a speed relative to the speed of light. So if there is a cosmic speed limit per se, for the speed of light, which is about 300,000 kilometers per second, if you're moving close to that speed, what happens if you do something that tries to go faster? What if you move it along faster? The answer is you can't go faster. It's that the area or the object or the matter changes in the way it behaves. And there are some fascinating, very cool parts of this. And the three of these that are mentioned on 445 that I'll just go through briefly. And we don't have time to cover this in great detail. And if you're interested in Einstein's theories of relativity, I highly encourage you. Of course, I know you're going to read through this text, but there are lots of areas where you can get supplemental information on Einstein's theories here. But these three are pretty far out there ideas. But the fundamental results of special relativity that defy our everyday experience is this. The length of an object decreases as its speed increases. That is to say, an object will shrink down if it goes fast enough. That's a far out thought. The second one, clocks that you see moving run more slowly than the ones you see that are at rest. That is, if it's moving fast enough, time will actually slow down. This is a process we call time dilation, and it is a fascinatingly cool thought to think about. Could you slow down time? Very exciting thing to think about. And then the last one over here is that the mass of an object increases as it moves faster. So it's talking about the change in mass as well. All of these topics are things that if you've never seen or heard about relativity before, this sounds like I'm making this up, that this is not real. But all of these have been verified on very small scales, albeit. But there are some fascinating results of the fundamental properties of our universe that cannot be changed, one of which is that the speed of light is a constant. Now, I failed to mention there back here this idea of the clocks moving at a different time. This is what introduces, so we end up recombining the idea of time and space together. Because if an object is moving a distance and the time is changed, then we have this relationship where time and space must in some way be intertwined with one another. And that's the concept that this book and that many others call space-time. And general relativity tries to explain that space-time can be bent or curved, or warped, or distorted. And actually, it was Einstein who predicted this. And one of his great predictions, one of the big predictions, was this concept we call gravitational lensing. And it explains this over here on 14.3, this concept where they're talking about the light around a massive object is bent because of the gravity of a massive object, like, say, for example, a star. The object, the light, is being bent because gravity is bending that space-time. Very cool concepts to think about here, associated here with the beginning of chapter 14. Now, oh, and we have to talk about here. We see this idea. A lot of times, the idea is a good analogy is to think of a flat sheet, like a bed sheet or something. And if you were to put two bowling balls on a bed sheet, it would warp down into the bed sheet. Even if you kept it tight, they would press down in there and move around. And as they moved around, you would see these depressions moving around. Very similar idea to the curving of space-time. Now, how does any of this have anything to do with black holes? Well, the idea is that a black hole is so massively dense. This is more dense than a neutron star. It is the most dense idea, and the idea is it's so dense and so much gravity in such a small area that a particle of light, a photon, cannot escape from it. Right? So there becomes the idea why we call them a black hole. If we see objects, if we see something, if we see, a pen, because a particle of light is coming from the light in here and hitting this and going to you and hitting your eyeball, what you have to imagine is that the gravity of this thing, if my pen were a black hole, it's grabbing that photon and not allowing it to leave. That is where the name black hole comes from. Which really, when you think about it, is a fantastically cool idea. But on 14.5, they talk about actually a convenient concept is that we simplify. Matter becomes simplified when it is inside a black hole. And the first thing we need to look at is there are a couple of terms you need to go along with this that you're going to hear me use throughout the rest of the chapter. One of them is the thing we call the event horizon. And it says a black hole is separated from the rest of the universe by its boundary. This boundary is called the event horizon. And at that point, it says the event horizon is not like the surface of a solid liquid body. No matter exits this location except for the instant it takes falling mass to cross the event horizon and enter the black hole. And this, the size of this, the distance from the center, from the center is called the Schwarzschild radius. So there is a description of how big these things are. And they go through explaining how that all works. But the nice part of it is there are really only three things that we need to describe the matter inside of a black hole. The only thing that we have to worry about is angular momentum, mass, and electrical charge. Everything else becomes insignificant because of the effects of the black hole. So then they talk about on 451 that if you were to fall into a black hole, the effect would be an infinite voyage because time would be changed by the effect of the black hole. So it's a fascinating thought to think about. There's so many real mind experiments to take you through with this chapter. But the idea is, of course, remember that time dilation, time is being stretched out, and so we would end up, the voyage would effectively take forever, which is a wild, wild thought to think about. Okay, so if we can't see these things, if it's not emitting a light, it's not emitting a photon, how do we even know that this exists? I mean, we can't see the thing, so how could we possibly have evidence for it? Well, one of the ways we can do this, again, is by going back to these good old binary stars. Binary stars are really the astronomer's friend because we can see the behavior of an object moving around this black hole is going to be different. By studying the matter around this, and I need to explain this name. I realize I skipped this, but the idea is with a binary system, you're going to have different types of radiation being emitted that will give you clues there must be a black hole there. Now, before we can really understand that, we need to understand that if we have the black hole at the center, and this doesn't look like it's showing up terribly well on camera, but on 452, this area right around here is the event horizon. And they're using here some swirling water to represent this. But this black hole in the center there is sort of a point of no return, if you will, the event horizon. But around that, around a black hole, is this area we call the accretion disk. And the accretion disk is where all this material is being drawn in. And so effectively what we can see is we can see some of this stuff out around it. We can see the matter behaving differently and sort of through indirect processes get an idea of what must be going on to have this black hole be in the center. Now, stepping out a little bit further, we realize that a supermassive black hole, the largest of them, we think are probably at the center of galaxies, which ends up being a very useful part as we go through the end of this course, is we're going to be looking at the behavior of galaxies and how massive black holes play a role in that. So that takes you through the majority of the important parts for Chapter 14. Again, make sure you're going through the reading, check out the PowerPoint, and you should be good to go on the homework for this chapter. Good